Welcome to this explainer. If you've ever looked at calculus and wondered exactly how mathematicians take these wild, curved, complex shapes and calculate perfectly exact areas, well, it all starts right here. Today, we're going to unpack the foundational math that makes advanced integration possible. And we're going to treat this concept, the Riemann-Stieltjes integral basics, kind of like learning the absolute art of slicing.
All right, let's map out our journey for today. First, slicing the closed interval. Second, subintervals and their lengths. Third, finding the partition norm. And finally, refining the partition.
Let's dive right into part one, slicing the closed interval. Okay, picture an uncut loaf of bread sitting on your kitchen counter. It has a definite beginning and a definite end, right? But to really deal with the whole loaf, we have to cut it up. And that brings us to our very first key definition, a partition. A partition is basically just a mathematician's way of making systematic cuts along an interval. So if our interval starts at point A and ends at point B, our partition, which we just call P, is a finite set of points that divides it all up. We label these points starting at x sub 0 all the way up to x sub n. The very first point, x0, is exactly our starting line, A, and the very last point, xn, is exactly our finish line, B. When we draw this out, it makes total sense. You can visually see how x0, x1, x2, all the way up to xn just sit right there on the line. It's a really great way to see that a partition isn't some weird abstract concept. It's quite literally just placing markers down on a straight path to break a large journey into smaller, way more manageable steps. Now, here is a golden rule of partitions, and it's something you definitely want to keep in the back of your mind. A partition that creates n subintervals will absolutely always contain n plus 1 points. Think back to our loaf of bread for a second. If you want to create just one slice, you actually need two cuts, right? One at the beginning of the slice and one at the end. If you want two slices, you need three markers. So n slices will always require n plus 1 points. Moving right along to part two, subintervals and their lengths. So, now that we've made our systematic cuts across the number line, let's grab a magnifying glass. Each specific slice we've just created is called a subinterval. It's simply the individual segment, or the space, between any two consecutive cuts on our partitioned line. We write this mathematically using brackets, noting it as the space between x sub I minus 1 and x sub I. And honestly, that just means the point we started at and the very next point. Naturally, once we have a subinterval, we're going to want to know how big it is. To find the length, which we mark with the delta symbol as delta xi, we simply subtract. We take the ending point of the slice, xi, and subtract the starting point, xi minus 1. So the first subinterval's length is x1 minus x0. The second is x2 minus x1. And the pattern just continues. It's basic geometry, for sure, but it literally forms the bedrock of integration.
Which brings us to part 3, finding the partition norm.
This is where we introduce the ultimate test for our cuts. We call this test the norm of the partition, and it's denoted by these double vertical bars around the letter P. While the notation might look a little intense, the concept is incredibly straightforward. The norm is really just a fancy mathematical term for the largest, thickest slice in our entire partitioned interval. It is simply the maximum length among all the subintervals we've created. Let's pull this out of the abstract and actually put our new terminology to the test with a super concrete example. Imagine we're looking at an interval from 0 to 6, and we decide to use a very specific partition. P equals the set of points 0, 2, 5, and 6. Let's just walk through our slices step by step. Our first subinterval sits between our first 2 points, 0 and 2. Using our simple subtraction formula, 2 minus 0 gives us a length of 2. Our next slice is between 2 and 5. Subtracting 2 from 5 gives us a length of 3. And our final slice is between 5 and 6. Well, 6 minus 5 gives us a length of exactly 1. So when we map it all out and look at our 3 distinct subintervals and their lengths, which are 2, 3, and 1, finding the norm is a breeze. We are literally just scanning that length column for the absolute biggest number on the list. And there it is, it's 3. Because 3 is the maximum length out of all our calculations, 3 is officially our norm for this specific partition. Seeing it written out like this really grounds the concept. You've got the number line at the top visualizing the jumps, a jump of 2, a jump of 3, and a jump of 1. And then right below it, the exact equation. The norm of P equals the max of the set 2, 3, and 1, which equals 3. meaning the absolute widest gap anywhere in our partition is exactly 3 units wide. And finally, part 4, refining the partition. This brings up a really practical question. What happens if our cuts simply aren't precise enough? Like, what if a gap of 3 units is just way too wide for the level of mathematical detail we actually need? Well, we can create what's called a refinement, denoted as P star. A refinement is exactly what it sounds like. We're refining our original work. It's a brand new partition that contains every single point from our old partition, P, but we just sprinkle some extra points in. The rule is simple here. You can add new cuts, but you absolutely cannot move or remove the old ones. Well, let's highlight this with a quick comparison. Say our original partition P was just the points 0, 2, and 6. To create our refined partition, P star, we keep 0, 2, and 6 exactly where they are, but we decide to drop a brand new point right at the number 4. So our old partition had 3 points, our refinement now has 4. What's really cool is how visualizing this brings the whole concept home. Look at the setup for P, with that massive gap between 2 and 6. Then compare it to P star. By adding just that single extra point at 4, we force that giant subinterval to break right in half. The slices are getting smaller, tighter, and so much more precise. And this is exactly why we learned this in the first place. We now know how to slice an interval, measure those slices, find the largest gap, and add more points to refine our cuts. But I want to leave you with a provocative thought here. What do you think happens to our partition's norm as we add not just one, but infinitely more points into our refinement? As you picture those gaps shrinking down to almost nothing, well, you are standing right on the doorway to true integration. Thank you so much for joining me for this explainer on the Riemann Stieltjes Basics.